Okay, now we start our next topic, which is Bayesian games. So the idea is that Bayesian games are an extension of normal form games where we have some kinds of explicit beliefs about what's happening. So specifically, up until now, it's been implicit in game theory for all of the kinds of games we've talked about that the game that we're playing is common knowledge. So specifically the rules of the game, the structure of the game, and also the preferences of the players, or equivalently the payoffs of the players, have all been common knowledge. What common knowledge really means is that all players know it, and all players know that all players know it, and all players know that all players know that all players know it, and so on, all to infinity. This is I haven't gone into a lot of detail about this, but this is sort of implicit in the justification of Nash equilibrium, or rather, Nash equilibrium is describing the situation in which that common knowledge is valid. So this situation where everything is known is called complete information. So to be clear, there's a kind of confusing coincidence of terminology. You shouldn't confuse complete information, which is common knowledge of the structure of the game, with perfect information, which is when players completely observe the state of the game, the state of an extensive form game while the play unfolds. These are totally different things. So imperfect information is where we have an extensive form game with information sets. Incomplete information is a much harder thing. That's what we want to go towards. We want to go towards incomplete information where we're modeling a situation where players are uncertain. Bayesian games are a specific approach to this where you have uncertainty specifically about payoffs, but not about the remainder of the structure of the game. So specifically, each player is going to have a thing called a type drawn from a fixed list of several possibilities. And every player is going to know their own type, but have probabilistic beliefs about the types of the other players. And we're going to have a setting where types can only affect payoffs, not other things. So we're going to have a situation where the structure of the game is common knowledge, but payoffs are not common knowledge. So here's the definition of a Bayesian game in normal form. So we're going to have n players. So this is an extension of normal form games. So it consists of a normal form game kind of with more information attached. So every player is going to have a set of moves, same as before, but they're also going to have a set of what's called possible types. This is a bit like personality types, I think, this word. And then we're going to have a prior, which is a joint distribution on all types. And this prior is going to be common knowledge. So what this means is that because we have a prior joint distribution, when a player learns their own type, they gain additional knowledge about the types of the other players. So they're going to do Bayesian updating, and they're going to attain a posterior distribution on the types of other players, which is going to be their belief. And then the last piece of information specifying a Bayesian game is a payoff function that says that for every combination of moves and also for every combination of types, we get a payoff vector. So everyone's payoff can depend on all the moves and all the types. Okay. If we talk about what strategies for these things can be, so I've said informally that every player is going to know their own types. That is to say, every player is going to make an observation of their own type. And if you remember our old principle that a pure strategy should be a function from things you can observe to things you can do. So what that means is that a strategy for player I should be a function from all of the types that player I could have to all of the moves they could make. So it's to say, for every thing that player could believe, they know what they could. This says what they will do. So a pure strategy profile is going to be a tuple of one of these for every player. So we're going to have This is the set of pure strategy profiles. We can also talk about mixed strategies. So mixed strategy is just going to be, as usual, a probability distribution on pure strategies. So a mixed strategy profile is going to be a tuple where the ith thing is a distribution on functions from player-wise types to player-wise moves. Okay. Having said all of that definition, it's quite often very convenient to draw Bayesian games like as though they're in extensive form. So the prior distribution on types, we can kind of pretend that it's a move of nature. We can depict it the same as if it's a move of nature, and then we use information sets to depict how every player can only see their own type. This is sort of an informal abuse of notation, but it's extremely useful. So here's a kind of typical example. So here we have two players who can be type 1 or type 2. So this is a bit small, but both players are type 1. This is player 2 is type 1, player 1 is type 2. This is player 1 is type 1, player 2 is type 2. This is both players are type 2. And then I've set up the information sets here so that player 1 knows their own type when they make their move, but they can't see player 2's type. Player 2 can see their own type, but they can't see the type of player 1, and they also can't see the move of player 1. So this is, I've left the payoffs blank because this is kind of a template for a 2x2 Bayesian game with two payoffs for each, two types for each player. So to be clear, when I say that this is a shorthand, I mean that we have a sort of normal form where we turn this extensive form game into a Bayesian game. Now, there's a caveat that this is not the same thing as when we normalize an extensive form game of imperfect information to a normal form game. Because when we do, so previously when we've defined normal forms for this kind of thing, one of the things we have to do is to take expected payoffs over all of the nature moves. That's for a normal form game, but for a Bayesian game, we don't do that. This distribution becomes part of the definition of the game. So in the next video, I'll show you a more specific example of this. So this thing, if I was turning this into its normal form as a Bayesian game, I'm going to say that every player has two moves. So we have x1 and x2 are both two elements, and also both players have two types, which are type 1 and type 2. So theta 1 and theta 2 are both two elements. And then this common knowledge prior, which is part of the definition of the game, comes from the distribution, the strategy for nature. I haven't drawn it, but of course a move of nature in a extensive form tree comes with a probability distribution attached to the edges. So that becomes the prior, or rather we use this to depict the prior.